My humble salutations to my beloved Bhagwan, respected elders and my dear students. Hearty welcome to number 3 class, unit number 5. We are going to learn about the quadratic reciprocity law. Reciprocation. What is the reciprocal of 1 by 2? That is 2 by 1. What is reciprocal of p by q? Q by p. So similarly here we are going to show that the legendre symbol p by q into legendre symbol q by p becomes equal to minus 1 whole to the power of p minus 1 by 2 into q minus 1 by 2. So once again, legendre symbol p by q into legendre symbol q by p equal to minus 1 whole to the power of p minus 1 by 2 into q minus 1 by 2. The proof is very simple. By theorem number 8 we have learned that if p is an odd number and a is an odd integer, and further if GCD of a comma p equal to 1, then we have legendre symbol a by p equal to minus 1 whole to the power of summation integral part of ka by p, k running from 1 to p minus 1 by 2. So applying this equation, this symbol value to p by q and q by p legendre symbols, we have p by q into q by p equal to nothing but minus 1 whole to the power of summation kp by q, k running from 1 to q minus 1 by 2 into minus 1 to the power of summation integral part of kq by p, k running from 1 to p minus 1 by 2. Because the bases are the same, we can add the powers. So minus 1 whole to the power of this becomes summation q minus 1 by 2, k running from 1 to q minus 1 by 2 into integral part of kp by q plus summation integral part of kq by p, k running from 1 to p minus 1 by 2. So we are going to prove that the powers p minus 1 by 2 into q minus 1 by 2 is equal to summation integral part of kp by q plus summation kq by p. In the first summation, k running from 1 to q minus 1 by 2. In the second summation, k runs from 1 to p minus 1 by 2. Now in order to prove this, we are going to have the construction, that is, we are going to have a rectangle. So here this is explained with an example. Actually in the examination you did not write directly, we can write the proof of this. So we are going to consider, that is, directly you can come to this. Consider two distinct odd primes. Consider the rectangle plane xy plane with the lattice points xy bounded by the points 0 0, capital A p by 2 comma 0, capital B p by 2 comma q by 2, and capital C 0 comma q by 2. So with the condition that x varies from 1 to p minus 1 by 2 and y runs from, that is, 1 to q minus 1 by 2. The total number of lattice points are equal to p minus 1 by 2 into q minus 1 by 2, and no point lies on the diagonal line, that is y is equal to q by p into x or py equal to qx, joining the points 0 0 and p by 2 comma q by 2. As p is not equal to q and p comma q are distinct points, T1 is the region below the diagonal OB and T2 is the region above the diagonal. Here it is a print mistake, it is written as below, but it should be above the diagonal line. So in the region T1, so we are having, that is equal to, that is, we are having points, that is, if you consider 1 less than or equal to x less than p minus 1 by 2, and then automatically y lies between 1 and qx by p. Therefore the total number of lattice points in T1, the region, is nothing but summation qk by p, k running from 1 to p minus 1 by 2. In the region T2, that is where the y lies between 1 and q minus 1 by 2, the value of x will lie between 1 and py by q integral part. So the lattice points in T2 are summation pk by q, k running from 1 to q minus 1 by 2. Therefore totally the final total number of points p minus 1 by 2 into q minus 1 by 2 are nothing but summation qx by p, k running from 1 to p minus 1 by 2 plus summation integral part of pk by q, k runs from 1 to q minus 1 by 2. Therefore, by Gauss lemma, p by q into Legendre symbol p by q into q by p equal to minus 1 whole to the power of summation q minus 1 by 2 in integral part kp by q into minus 1 to the power of summation kq by p, k runs from 1 to p minus 1. So finally we get p by q into q by p equal to minus 1 whole to the power of p minus 1 by 2 into q minus 1 by 2. Thank you for watching this video.